use the mouse to point?
Yep, you should. Yeah, you should be able to use mouse point, and you can tap all.
And it's that one.
Yeah. Great.
Sorry.
Well, it's okay. This is very much experimental talk, if you like. This is very much work in progress. And so I'm hoping you'll be a friendly audience and you'll come up with some of the answers that I'm struggling to get. So what I'm anxious to understand, I want slideshow. Why is it not doing slideshow for me?
Hit F5.
F5. Oh, brilliant. Okay. I'm looking at layering. So this is a micro-rhythmic layering, inch scale layering that is in the Skaergaard Intrusion in particular. And I'm going to suggest a totally new mechanism for this kind of self-organization. Right, so here's the Skaergaard. This is pointer work. Yeah, here we are. Just to give you a sense of scale, we've got about 8 kilometers this way, about 6 kilometers that way, or is it 11 and 8? It's about 4 kilometers thick. It is formed from a single injection of magma. Well, lots of little ones, but sufficiently closely spaced that they can be thought of as a single injection, and it crystallized as a closed system. And you've got the layered series accumulating from the floor upwards, the roof series coming down, as was mentioned earlier, it's about 700 meters thick. And then we've got the wall marginal border series here. What we're going to be looking at in particular is the upper part of the layered series, UZA, which is where this micro-rhythmic layering occurs. So we've got progressive fractionation here. We see it, evidence for the interstitial liquids splitting into 2 immiscible conjugates around about this level, but the bulk magma doesn't become immiscible until we get up to this point here. And this will become relevant later on. So this micro-rhythmic layering is most widespread in upper zone A, although you see isolated examples lower in the stratigraphy. It's spaced 2 to 3 centimeters, and you can see it here. It's rather poorly defined, but it's superimposed on a larger scale modally graded packet. So just for scale, there's my GPS there, just to give you an indication of scale. And again, here you can see there's a very weakly defined modally graded layer going from the base here up to the top, and we get this micro-rhythmic layering that's superposed on top of it. So there's another little set of layers there. Now, I should say that this layering is really very poorly defined. So when you're standing and looking along it, you can see it very clearly here. There's my notebook for scale. It's very, very clear. But this is me just zooming in on that photograph. And you can see if you're actually looking at it with the hand lens, it's very, very weakly defined indeed. You get these rough patches here. So it's not a continuous layer at all, poorly defined. And as an example of that, I collected a nice sample of it and brought it back to Cambridge, and I put it on my, my desk, and I thought, oh shit, I can't see the layering at all. And I got really upset thinking I'd made a really stupid mistake here. I collected the wrong stuff. And then I went out to get a cup of coffee. And as I walked into my room, I could see it from 4 meters away. And there was the layering. You could see it really clearly. So I got some sticky things, and I basically put dots on where those layers actually are. So they're actually coming down like this. And in this photograph, you can't see them. But I promise you, if it's 4 meters from you, you can see them very clearly. So they're very, very poorly defined. And if you just, you know, if you were just to take a slice across here, you can see that you would miss some of those layers because the mafic bits just aren't absolutely continuous. And so with this slice that I've got, this is the same scale. So these are centimeters coming along here. You can't actually see that layering very well defined at all, but it's definitely there. Okay, so how on earth does it form? Well, there are 4 mechanisms that I could find in the literature that have been suggested for plutonic igneous rocks. This sort of self-organization forming these sort of fine-scale layers. So the first one is oscillatory nucleation and growth. And this was the very first method that was suggested by Liesegang, in fact. of how to make these patterns, precipitate patterns we've got here in a layer of gelatine. And essentially you've got two diffusing components, and when they react, they precipitate a bunch of crystals, and then you have to wait for the diffusion to happen again because it's used up one of the ingredients before it can precipitate again to make another layer. And another good example here of these Liesegang bands that you get in doing diagenesis of a sandstone. So you've got water trickling through the sandstone and it oxidizes a little layer of iron oxides. And then you have to wait for more water to come through before there's enough reactants to make the next layer along. So that was the very first way of making, or the first suggestion for making very, very fine scale self-organized patterned layers. But unfortunately, we can't apply that in Skaergaard because what we're looking at is not in situ nucleation and growth on this on the floor of the magma chamber. What we've got is the layering is superimposed on a modally graded layer that was clearly a sedimentary feature. So we've got crystal accumulation and then the layering is imposed. So that doesn't work. The next thing is competitive particle growth. So I just stole this diagram from one of Alan's papers. So in order to get competitive particle growth, what you need is a grain size gradient. And so it's driven by the fact that larger grains are more stable than small grains. So when you've got a grain size gradient like this, those large grains here see smaller grains there. This is just like school playground bullies, right? They start dissolving them and eat them up and they become bigger. And then you're left with a layer without any particles. And these ones here are now very, very small. So these ones here start eating up those ones. And you're going to end up with a series of layers of large particles divided by particle-free layers. Now, in order to make this work, Ostwald ripening needs long times and small grain size. So you need a mechanism to have your plutonic rock where you can reduce the grain size, and it's very, very slow cooling, and it's superimposed upon an overall grain size gradient. Now, probably the prime example of this is a photograph that Alan took, is the inch scale layering of still water. Now, this is absolutely classic locality. It's about 60-meter long traverse across the Stillwater intrusion along a road, and you get these beautiful paired doublets in an anorthosite where the dark layers are pyroxene rich. And the idea is that the competitive particle growth was triggered, A, because the still water cooled fantastically slowly, and B, you could have a reduction of grain size due to infiltration of metasomatic fluids, which triggered some sort of partial melting and a melt back and a grain size reduction. So Alan's done some very nice numerical modeling of this and can generate these doublets by competitive particle growth. So I looked at the microstructures in here and they totally fit with this model. First, there's abundant evidence for slow cooling. So plagioclase grain shape is linked to cooling rate. The lower the aspect ratio of the plagioclase, the slower it grew. And we can clearly see that the plagioclase is almost equant in these rocks. Secondly, where there is no second phase in the pure plagioclase regions, we've got beautiful granular microstructure, which is very, very slow cooling in the subsolidus. So it effectively becomes like a metamorphic rock. And you can see that very, very beautifully here. The other thing that you can see is that in some of these plagioclase-rich regions, the grain boundaries aren't nice and smoothly curved. You can get them really irregular like this, but the irregularities are pinned by thin films of pyroxene. So we've got pinning during grain growth, which again needs slow cooling in the subsolidus. But what's interesting is that we commonly see these little cusps of clinopyroxene on the plagioclase grain boundaries, and I'm pretty sure that they're pseudomorphing a texture equilibrated melt-filled porosity, which again says really slow cooling. And interestingly, what it also says is very high permeability, because if you've got a low dihedral angle, which you have for melt plagioclase, then you've got total interconnectivity of a melt phase. So we've got very slow cooling, which is what we need. We've got very high permeability, which is also what we need for effective mass transport. And the other thing, which is really nice, is that when you see the clinopyroxenes that have been enclosed by later crystallizing orthopyroxene, the smaller they are, the more rounded they are, like these ones here. So that's the other signature for Ostwald ripening, because as grains dissolve, they become rounded. So the small ones are rounded and the large ones are more euhedral. That's absolutely the key indicator for Ostwald ripening. So we've got all the evidence there to record this sort of activity of competitive particle growth for this microstructural self-organization. I looked at some other interscale layering from other intrusions. This is one from the Bushveld. This is an orthosite with chromite layers, and that's just a thin section scan, which gives you an idea of the length scale of the layering. And we see exactly those microstructural characteristics that we saw in the Stillwater examples, where we've got very low aspect ratio plagioclase, and we've got little pseudomorphs of the texture equilibrated melt field porosity. So again, very, very slow cooling, melt solid textural equilibration, giving us a high permeability. And critically also, we have a very, very simple mineralogy. We've just got 2 phases essentially, or 3 at most, in these rocks. So those are the key indicators for self-organization, interscale layering formation by competitive particle growth. Right, so simple mineralogy, grain size grading, which is inferred. We can easily do it with melt back from this open system Stillwater example. We've got very, very slow cooling rates, and we've got this high permeability and effective mass transport. That all works for Stillwater and Bushveld, but it doesn't work for Skaergaard. It's very notable that the modal graded layers, these metric scale modally graded layers on Skaergaard, have not got a grain size gradient. That's been known for decades and decades. There's no grain size gradient. We've got no mechanism for reducing the grain size so that Ostwald ripening becomes important because it was a closed system, unlike Bushveld and Stillwater. We've not got any of those microstructures indicative of slow cooling and melt present texture equilibrium. It just doesn't work. Okay, so we can't invoke competitive particle growth for the Skaergaard example. There's a third patterning mechanism, and that's that we get reorganization, sort of modal reorganization that's driven by reductions of grain boundary energy. Now, this is sort of like texture equilibration, but it's based on the premise that grain boundaries between 2 grains of the same phase, AA grain boundaries, like these ones here, have got a lower energy than grain boundaries between 2 minerals of different phases, which is AB boundaries, so these ones here. So if that's the case, and the rock has got enough time to sort of mull over its past misdemeanors, what it's going to do is recrystallize so that you end up with monomineralic bands, because by achieving that, it reduces its overall energy. Okay, so it's based on this premise that the AA grain boundaries have got a lower energy than AB grain boundaries. Now, there's a very, very easy way to test that, and that's because the geometry of 3 grain junctions is governed by the ratio of these 2 things. Now, if this holds true, if these AA grain boundaries have got a lower energy than AB grain boundaries, then this value here has got to be greater than 1. And in that case, the dihedral angle is going to be greater than 120 degrees. Okay, so all we need to do is measure some dihedral angles in texture equilibrated rocks. Now, this has been done in metals for more than half a century. So the classic paper on this is Smith, 1964. And the title kind of is a very ironic title because he says it's some elementary principles, but actually this is the bedrock. This is the fundamental paper that actually sets out an awful lot of the microstructural work that was subsequently done in materials science. So it's almost like false modesty. But what he did here was he measured dihedral angles and interfacial energies in some common alloys. And you can see this great table here. Most of them are copper alloys, but he's got some tin zinc down here as well. And this is the ratio of those 2 grain boundary energies. And I've highlighted in green the 2 which have got the AA grain boundaries being lower energy than AB. And then there's another 2 here, which they're the same. So generally they're not, right? Which is almost completely counterintuitive. And Smith himself did remark that this was counterintuitive. So he says, in many cases, the two-phase interface seems to have a lower energy than that of the grain boundaries of the phases that are composing it, not higher, as perhaps might have been expected. And what's amusing is that there is no theoretical explanation yet advanced for this fact. He hasn't got a clue why this should be. That is still the case. No one has a clue why it should be. It's totally counterintuitive. Ron Vernon, though, in 1968, grabbed the Smith paper and thought, well, what do we see in metamorphic rocks? So this is his table here in metamorphic rocks, and he's just got the mode of the dihedral angle population is close to the true three-dimensional value. And you can see that most of them, again, are less than 120 degrees. So we've got the wrong way round. There are some anomalies. These 3 down here are the anomaly is actually very interesting, because these 3 here are of mineral pairs where the structure and composition of the 2 minerals is completely different, like calcite, olivine, for example. You've got a carbonate and a silicate. Apatite, quartz, phosphate and silicate. Those are exceptions to the rule. And then garnet's doing something interesting here as well. This is something I want to chase up, because again, these anomalies are telling us something very, very interesting. So the dihedral angle doesn't generally seem to be greater than 120 degrees, apart from some interesting anomalies, in which case this grain boundary energy thing actually acts against patterning. It stops it from happening. So the next question is, well, what sort of values have we got of dihedral angle of the minerals that are involved in gabbros? So I dug around in the mineral collections and found lots of fully texture equilibrated rocks containing the minerals that we care about. This is just a random one just to show you how nice it is. This is a spinel, also pyroxene rock. This is a granulite. We've got our 2 pyroxenes, plagioclase, magnetite. This is an olivine magnetite rock from Sierra Leone that's beautifully texture equilibrated. And then there's an olivine plad rock that's decently texture equilibrated. And what do the dihedral angles look like? Well, this was weeks of work. All of them are less than 120 degrees. So we cannot use grain boundary energies as our method for patterning in gabbros. It acts against it. The rock wants to stay so that each grain is surrounded by a phase that is different to it. So we can't do that. That's 3 down, 1 to go. The next, the fourth mechanism that's been invoked to form self-organization, layering, etc. in gabbros is compaction and shearing. So this is essentially treating them like a metamorphic rock. You know, gneisses are banded. So why don't we just assume that the same thing can happen in gabbros? Well, the example I'm going to use, you'll see why I'm talking about this apparently rather random example of layering in the Skaergaard. You'll see why it's important a bit later in the talk. So this is looking at trough bands in the Skaergaard. So trough bands are stacks of modally graded layers that form stacks of about 100 meters thick, and they're separated by ridges of homogeneous gabbro. And there are 2 theories to explain what they are. Neil Irvine's theory is that the ridges of gabbro formed long-lived channels down which you got crystal-laden flows being channeled in these things and dumping out modally graded layers. So they're essentially sedimentary. Whereas Alex McBurney and Alan suggested that, in fact, what we've got is localized compaction. So what we're seeing here, these layers here are actually like the equivalent of a gneiss. So it's all to do with compaction. Now, I disagree. You can see clear evidence of their sedimentary origin with simple things like sometimes the axis of the channel shifts and you get truncation of the layers. So there's one layer truncating here as the channel shifts this way, and then it shifts back the other way. You can see layer truncation, and then up here you get shifting as well. So the channel is shifting each time, and that doesn't fit with a compaction model. This is more a sedimentary thing. We also get nice evidence of overbank deposits, If you look at the microstructures, there's no evidence of any sort of compaction-related recrystallization. This is a plagioclase-rich part of one of those layers where the plagioclase crystals just look like sedimentary particles. So this is a ChemScan image where the plagioclases are these things here, and the slightly darker rims, this is an albitic overgrowth. Now, in a metamorphic rock, if you've got recrystallization and compaction, you tend to see evidence of growth. The recrystallization, sort of dissolution, reprecipitation will make these compositionally different rims will always have the same sort of orientation because we've been squashing it this way. Whereas here, the albite rims are just everywhere on the pore corners. There's no sort of spatial difference there. We haven't got any evidence of dissolution and reprecipitation. There's no deformation that would be indicative of viscous compaction. Or this black stuff here is quartz, which we'll get back to. Okay, so the microstructures say no compaction. There is, however, a very strong fabric in these troughs. So this is looking down the axis of one of the troughs here. And this is a paper that Stoyevich and I worked on some years ago now. And there's a very strong lineation of the plagioclase and apatite as well, and olivine, parallel to the troughs. Now, it has been suggested that this lineation is due to some sort of shearing during compaction, but that also can't be the case. So in this particular part of the stratigraphy in Skaergaard, it's upper zone stratigraphy, there are elongate plagioclase grains that are really rather noticeable. And you can see them here, elongate plagioclase grains. So it's these really that define the lineation in the trough axes. So this is just looking down the trough axis. We've got a slightly truncated version of these modal layers, and you can see the elongate plagioclase here. Now, these elongate plagioclases are lineated in the troughs. But if you go, this is a diagram from one of Neil Irvine's papers. If you go in these modally graded planar layers underneath the troughs, they form a foliation. And then if you go in the elongate ridges that separate the troughs, they're randomly oriented. Okay, so they're clearly there. They're not due to recrystallization during any sort of compaction. They're sedimentary particles. And that is really highlighted if you map out where they appear. So these are all the trough layers here. They were labeled by Wager and Deer from A to S, just in this region of the campsite. There's Homestead Bay, in fact, their little house that they lived in. They overwintered in it in 1936, is just about there. Okay, so these elongate plage suddenly arrive in the stratigraphy. They don't exist, and then pow, at this point here in the stratigraphy, suddenly they are there. And then they are really noticeable here, and then they fade out, and they roughly disappear around about here. Now, this is a paper that I'm working on. I'm thinking that what we've got here is that those elongate plagioclases are clearly sedimentary particles, and they suddenly arrive at this point here. And this also coincides with a break in the progressive fractionation seen in the wall mush. And I think what happened was that there was an earthquake, the wall mush collapsed, all this elongate plage material was dumped from the wall onto the floor. It changed the break in slope going from the wall to the floor, and then changed the convective pattern in order to trigger the formation of these elongate homogeneous gabbro ridges, and therefore the trough bands. Okay, so they're clearly nothing to do with compaction. The trough bands themselves are very definitely sedimentary features. The other bit of evidence that we're not dealing with compaction in order to make these layers is this very nice example in lower zone B, where we do see, what have I done? Help. Click on? Yeah. No. Oh, sorry. Right, this is a lower zone B modally graded layer. You can see it here. Absolutely lovely. Look at it. It goes from there to there. You've got the spacing very, very poorly defined, but there they are, about centimetric long. And we're going to follow this layer along. I always use this. It's got dual purpose. A, it's scale, and B, it stops you asking me horrid questions afterwards. Right, so here is the layer coming along here. And can you see there is a roof block. This is a roof block xenolith. And we're going to follow along. There is the layer right underneath it. And it is not patterned. So this layer has been compacted. We know it has because it's thinner here, because it's got a great big roof block sitting on top of it, and the layering has gone. So compaction actually stops the layering forming. Okay, so clearly this layering only forms in a mush that hasn't been compacted, and it's got lots of liquid in it. Okay, so that's new. So we can't use compaction and shearing. We've gone through all 4 possible mechanisms for forming microscale self-organization related layering. So we need to come up with something else. And this is where I just jump back to the trough bands. So this is one of the trough bands here. You can see the layers here. And we're going to zoom in on this bit. You can see individual packets coming in here. There's about 4 or 5 packets. You can see their mafic bases. And we're going to zoom in on that bit. And can you, this is again to frighten you off. There we've got self-organization within the trough layers. Each one of these individual little depositional packets has self-organized. We can also see it here. This is another one of the trough bands. You can see it here, very, very, very poorly developed. It needs a modally graded layer, and it mustn't be compacted. It must be nice and fluid rich, and you get this layering. So we need modal grading, and we need high porosity. There's another one here. You can see it's sitting in a channel. So we've got layers coming along here, and then the base of a modally graded layer, and you can see the superimposed micro-rhythmic layering. There again, you can see it's looking at it from another angle. This is a primary sedimentary event, pouring down weakly modally graded material with high porosity, just dumping it down, and then superimposed on that, we get the patterning. So this is my theory, that what we're seeing is a superimposition of patterning on this modally graded layer due to the differential migration of unmixed immiscible liquids. So we know we've got this in Skaergaard. This is a photograph from lower zone C, where we've got a little pocket of late stage liquid, and it's unmixed. And the dense iron-rich liquid has gone down here with a bit of disruption of the underlying mush. And then this is the silica-rich conjugate that's floated to the top and crystallized as an anorthosite. Well, not really an anorthosite, but very, very plage-rich. So we've got these 2 liquids, 2 immiscible liquids in this mushy layer. We can see the evidence for them microstructurally. This is a thin section. So that is a little pocket of iron-rich liquid. It's now made a very ilmenite-rich intergrowth pocket. And there is our silica-rich liquid, which is crystallized as a granophyre. Now, what's interesting, and I think what is driving all of this, is the fact that these immiscible conjugates have different wetting properties. So this is just an image of an experiment. The silica-rich liquid, which is this grey one, wets plagioclase preferentially. It wants to sit next to plagioclase, whereas the iron-rich liquid wants to sit next to oxides, obviously, and other mafic phases. So you can see here, this is the iron-rich liquid. Look at this low wetting angle here. It's hugging really close to that oxide grain. Similarly, these blobs here, the iron-rich liquid, yes, it's sitting on the plagioclase, but it's got a high wetting angle. It doesn't want to be there. So we've got these 2 liquids, and they've got affinities for different components of the mush. Silica-rich liquid wants to be near plagioclase. Iron-rich liquid wants to be near the mafic phases. So there's going to be some kind of positive feedback there, particularly because the silica-rich liquid crystallizes predominantly plagioclase. So it crystallizes more of what it wants, whereas the iron-rich liquid crystallizes very little plagioclase and mostly crystallizes mafic phases and oxides. So we've got a positive feedback there. And the evidence for this comes actually from some of the non-patterned modally graded layers in these trough bands. So this is trough band G, and you can see these modally graded layers are what Neil Irvine calls bipartite. They're not smoothly modally graded. They are bipartite. You've got a mafic layer and then a felsic layer, black, white, black, white. So this is just a scan of one of those modally graded layers, bipartite. So there's the base and there's the top. It's in 2 parts. And we're just going to zoom in on this bit here. Now, remember that these are being deposited by currents. So they get sorted in the current in a nice way that Neil Irvine explains, to bipartite layers, a bipartite mush. But there's going to be porosity in this mafic layer. Okay, the primocrysts there are pretty much all oxides and mafic phases, but there is porosity, and that porosity will crystallize. Why is it that when we actually look at the porosity in that the basal part of that bipartite layer, it is actually a pure adcumulate? There is no plagioclase in there at all. Well, there's a teensy weensy bit, there's a bit. You know, you have to look pretty hard for it, and there's a bit. So this actually crystallized as an adcumulate. All the silica-rich liquid that might have been there has left. And I think what we're seeing here is the migration, differential migration of your two liquids, driven both by gravity, because the iron-rich liquid is dense and so is going to go down into here. Silica-rich liquid is going to go up, but also by capillarity. Because the wetting angle for the iron-rich liquid is low here, it gets sucked into that layer by capillary forces. And the silica-rich liquid likewise gets sucked into the plagioclase-rich layer. And that sets up a positive feedback, because the iron-rich liquid getting sucked into here crystallizes more on the, it overgrows the olivines, the oxides, making the pores smaller, which makes the capillary forces even stronger. So you end up with losing all your silica-rich liquid and getting pure adcumulus growth in here. Differential migration driven by gravity and capillarity. And this is the corresponding layer at the top. You've lost all your iron-rich liquid because it's been dropped down by gravity and sucked in by capillarity to the basal layer, and you're left with your quartz stuff up here. So we know on that small scale, in those bipartite layers, we do have very rapid and very effective separation of those two liquids. So what we've got here, this is just here, we've got adcumulus growth and amplification of any modal grading in the bipartite layers, driven by, I can't point at this bit at the top because of this thing coming up. Never mind. Okay, it's driven by gravity and capillarity. Okay, and that's what makes this really, really strong bipartite layer. So this is where I'm stepping out now of my comfort zone. This is my last slide. I say, right, okay, what happens if we've got a weakly modally graded layer with high porosity, in which the interstitial liquid splits into two, silica-rich liquid and iron-rich liquid? We've got positive feedback in that the iron-rich liquid wants to wet mafic grains, and once it wets them, it's going to continue growing them, making the pore space smaller, making it even more advantageous for iron-rich liquid to segregate into those layers. So my idea is that you've got this modally graded layer. It's got iron-rich liquid and silica-rich liquid disseminated equally throughout. Gravity makes the iron-rich liquid generally go down and the silica-rich liquid come up. They start coalescing to form planar layers rich in silica and rich in iron, and that reinforces the patterning and the concentration of the two liquids. Because we've got slow separation relative to fractionation, what we see in these modally graded layers, these patterned layers here, is what we don't see in the bipartite layers, which is evidence that the iron-rich liquid is actually coming out of chemical equilibrium with the primocrysts. So we get this rather fascinating microstructure here, which Charles Nielsen calls paragenesis 2, which is where you see the original clinopyroxene primocrysts are recrystallizing, and you get the development of rims of olivine as this iron-rich liquid is reacting with all the primocrysts that it makes. So this separation, this patterning is relatively slow to make these, slower than in the bipartite layers. So we get this patterning here. So this is a relatively iron-rich part, which is these mafic bits. And then you get the relatively plagioclase-rich part, which still contains all the different phases. We're not getting separation of the primocrysts at all. We're changing the amount of overgrowth by moving the differential migration of these two liquids. So that's how we do it. We've got solidification of the segregated interstitial liquid in these layers, amplifies any sort of modal changes. So superimposed on this modally graded layer formed by sedimentation, we get this patterning. Now it's totally new. So I haven't got a conclusion slide because my conclusion slide will be a massive, great question mark. But what is actually, I think what it's telling us, I mean, Wolf mentioned, that what we need to discuss is areas of new research. I think this is one of the areas of new research. There's an awful lot of literature out there about the differential migration of immiscible liquids driven by gravity and capillarity, but it's all applicable to sandstones, and the liquids are oil, gas, and water. Whereas what we've got is a polyphase mush, so we've added complexity, and we've got solidification. So we've got two liquids with different wetting properties. We've got a whole range of different crystals in the mush, and the whole thing is dynamic because it's cooling and crystallizing. What on earth is the physical behavior of a system like that? I mean, clearly it's got enormous implications for all mineralogy and all the rest of it, and we know nothing about it. So that's my big question mark. How on earth do we start solving this problem? Thank you.
Thank you very much, Marian. I'm sure all of this will provoke some questions and comments. Martin was first. Well, to get honest, so if this is driven by gravity, so these inch layers should always be horizontal. That's something you can.
Gravity matters, but I think it's the modal layering that matters equally because of the capillarity forces. So it's actually parallel to some of the channels. So you've got two factors. You've got gravity plus capillarity. So here, can you see, if it were gravity, these would be straight along, and they're not. They're seeing the modal grading. So it's teasing apart the effect of gravity, which effectively needs gravity acts sort of universally, but the capillarity is going to care about pore size and the relative distribution of the different phases. And the pore size is going to be a dynamic thing because you've got solidification going on at the same time. So teasing apart those two controls.
I can't grasp the capillary, whether you should have a preferred orientation. Is that all?
No, it doesn't have a preferred orientation. No. I mean, if you put a brick in water, then the water just comes up here. But if you had water on this side of the brick, the water gets sucked in this way. I mean, think of one of these terracotta plant pots. You just lie it in a bucket of water, and then the water just comes in all directions. It doesn't see gravity.
Alan?
Yeah, I've got a couple of questions, I'd expect. One is, what's actually driving the segregation of mafic and felsic phases? I mean, I can understand liquids moving, but you're saying that this started out as a largely mafic layer, but it had plagioclase in it, and it's now segregating into plagioclase and pyroxene dioxide-rich layers.
Are you talking about the bipartite layers, these ones?
Yeah, something like this. Yeah.
So the Neil-Irvine model is that you get sorting in the crystal-laden flow as it comes down from the walls and across the floor.
Yeah, I'm not going to think of that. But
yeah.
So you're saying that everything that we're seeing here is all sedimentary?
No, I'm saying it's been amplified from the sedimentary. So in that mafic layer, there were no, in this particular section, there were no plagioclase primocrysts. But the interstitial liquid, I mean, the porosity could have been 30%, 40%. So if there'd been no differential migration of liquid, you would expect some plagioclase interstitially there, and you have none.
Not unless they're all lost later on.
Yeah, but there's no way to lose them later on.
Well, I would disagree with that. But then again, getting back to your other your free energy surface energy effects here. If you have a strongly idiomorphic crystal that always wants to form, say, a cube or whatever it wants to form, would it not really pay much attention to what the surface energy is of those around it?
Which minerals would want to be idiomorphic in that way, though? I mean, the texture equilibrated shapes of
chromite.
Yeah, but chromite does get quite rounded if you let it texture equilibrate.
Yeah, but they're basically sort of always sort of that. They aren't kind of squeezing into little cracks and crevices that you see in all the other minerals do. Silicates against silicates. So then that means that there might be something internal to the chromite that is causing it to be more idiomorphic than just the surface component alone. Surface energy.
Yeah, it's basically getting down to the crystalloblastic series of metamorphic rocks.
Yeah.
Yeah, which I don't fully understand.
Yeah. I think it's hard.
Okay.
Okay.
Oh, and the one last thing here.
No, last thing. That's it, yeah.
One last thing here. You keep kind of talking about the paper I did with McBurney, we talked about compaction and that kind of stuff here. But actually we didn't, compaction was just the reason to have liquids moving through the system. We didn't really care in terms of what was driving the segregation. It was not compaction driven. It was not because of compaction.
Okay.
You could just simply have, you know, an interstitial convection, if you will, and the same thing would happen. And you could actually have it without it, and it would still happen, but it wouldn't have a directional component.
Yeah. Yeah, the problem with that though is that you need relatively thick mush for that sort of compositional convection to happen. And we don't really have it by upper zone A in Skaergaard. Most of the floor is, the mush is only a couple of meters thick from dihedral angle. Well, you'd have to explain my dihedral angle observations for that, how you get the step.
Oh, yeah, one last thing. These are in troughs.
Yeah.
Why doesn't the liquid all just pond at the bottom of the trough?
Well, it probably does. I mean, if you look at the patterning in the trough layers, I can't remember which way around I go. The patterning is only in the axis of the troughs. There.
Yeah, but I mean, but you know, if you got these things are occurring on a scale like, let's say like this, it seems to be all the liquid, assuming that it can't just drain out the bottom, would form a horizontal flat layer.
But it doesn't.
But it doesn't.
No.
Okay.
All right.
Matt?
So I mean, terrific talk, Marian, and I really like the idea of these, the wetting behaviour playing a big role in controlling the migration of these fluids. I was kind of interested in, when do you think that you get that segregation? When do these immiscible liquids form? I mean, are you envisaging them being present all the time and maybe one being bubbles in the other, and then a separation occurring in once they're in the mush, or are you seeing them, this immiscibility developing much layer?
It depends where you are in stratigraphy. So if you're in upper zone B, the bulk magma is in mush. So it's there right from the start.
Okay.
The lower down you go, the more crystallization you have to have before you hit the binary. But here you're really close to it. This is upper zone A, really, really close, tiny bit of crystallization, then bam, it's on mixes.
But you show these scale layering also in lower zone B.
Lower zone
Is
B, they're
this
really
because
rare.
there you are further away from liquid immiscibility. This is a challenge for your models. Okay.
They're very,
And
very
then we
rare.
have Ivan, and then Freddie, and then and then there.
Thank you very much. I was really impressed by the presentation, and I love this idea. But one question strongly bothers me. It's a problem of mass balance. So if you imply that these conjugate liquids were both silicate liquids, so why do we have only magnetite in this mafic layers and this interstitial mineral? So was this liquid completely devoid with alumina or phosphorus, for example?
It's not only magnetite, it's crystallizing olivine and pyroxene as well.
So this is okay. I understand. Thank you.
In the particulars enriched layers, any homozonation? Because I would expect that this calcium fluid amount which is drawn into these layers, is that in the bipartite layers?
Yeah, this is from one of the bipartite layers.
Layers.
Yeah.
At the end, you also see that sort of zonation.
Well, this is from one of the bipartite layers. I haven't looked at the interscale layering ones yet. So this is the bipartite one, and you can see that this is the original particle, sedimentary particle, and then that's the overgrowth from the liquid.
Because if I understand your model correctly, you repeat that you have this homozonation.
Yes.
If you have this
Yeah.
more evolved
Yes.
calcines.
Yes.
Something.
Yes, absolutely.
Just that there was some general thoughts around those prompts and that sort of thing, and you talk about capillarity. I'm not, a research or specialist scientist, but was sort of thinking about those troughs and the way that the felsic layers, they sort of become thicker and disperse up to the peaks of the banks there. So is that, in essence, felsic layers escaping, whilst the more mafic layers are like becoming lifted or sustained against those walls by capillary action and that sort of thing.
Well,
That you then texturally you develop those random layers as the felsics escape versus more laminar sort of towards the margin. I don't know.
Well, the overbank deposits that are very obvious in some of the troughs are predominantly plagioclase rich. But so what we're dealing with is magmatic sedimentology. So it's not just like normal sedimentology where you've got particles, because we've got cohesion in a magmatic system. So some of these troughs have actually got primary dips of 40, 50 degrees. And it's not enough is known about cohesion between crystals. If the flow is coming down through these really steep layers, how easy is it for things just to stick there? I mean, do they stick immediately before they, as they touch?
Yeah.
But nobody's really done anything like that with cohesion in these modal bodies.
Yeah. Moving, it's the felspar escaping out of the layers.
No, I don't think it's escaping. I think it's a depositional thing.
Well, Holness, I really like your stories, but I just thinking the fluid dynamic. I think the parent magma is the salt. Yeah, if the parent magma is salt, its viscosity is high, and the flow, horizontal flow is maybe belongs to the laminar flow.
Definitely.
Yeah, if this is laminar flow, it will not have the enough energy to carry so many minerals for flow, maybe kilometer scale transport. It is maybe because for the maybe I think the turbulent flow it can carry so many minerals.
It's a balance between the Stokes settling velocity and the speed of the flow.
Maybe landslides.
Yeah, it's a landslide.
Yeah, coming up, so.
Yeah.
There's also, I mean, there's got to think the density contrast between sediment and water is potentially much greater than it is between crystals and magma. So yeah, your Stokes settling velocity is much slower. You don't need so much flow energy.
I think there is a different viscosity. One viscosity is for the silicon melt. And another thing is we thinking the from magma flow, which we thinking the viscosity of the magma. The magma contain silicon melts, and we also contain the minerals, maybe lithicals. And if we add maybe 10% or 20% of lithicals, the viscosity of the magma, not the melt, of the magma will increase very quickly.
Yeah, but if the density of the plagioclase is very, very similar to that of the liquid, it's not going to, the plagioclase isn't going to segregate. It's just going to get carried along. So it's a density difference that matters as well.
Okay, Bryce? Okay.
Marian, I think I read in this abstract by Iliadis that the viscosity of the silica-rich immiscible liquid is higher, 3,000 times higher than iron-rich. So if this flow, then I think moving will be the same thing. So this the silica-rich liquid will move 3,000 times slower than iron-rich. Does this has an effect on the layering? Have you thought about that?
Not yet. It doesn't affect capillary forces though, which is not affected by viscosity. Capillary forces just go with the pore diameter and the wetting angle.
This process too has something to do with this one.
So what's interesting? So Mary, in your model, I mean, I guess once we get to upzone B level, where the main magma, the assumption is the main magma is dissolved into the two liquids. So the in-scale layering would not form in that upper part, is that correct?
See any of that?
But
I don't know why it wouldn't.
but that would that be a test of your model?
No, because all you need is an emulsion in the interstitial liquid, whether it was there right from the word go, or whether it had to crystallize a tiny bit to form, I don't think that matters. But I haven't seen any interscale layering, but I haven't done much work on it. You have, though.
I'm trying to scratch my head. Clearly, this inscaling is more dominant in the upper zone A, but I think it also continues into the upper zone B. But
We need to get back then.
Well, Larry,
we have to go back.
B and C is getting poorer and poorer. If you
It does get poorer. It's more
the best player
dominant in
is
upper zone B.
from upper zone A down.
Just a quick one, how different is this iron-rich liquid from the magnetizing crystallite? Is it gonna crystallize a lot of magnetite, or is it gonna be other mineral? I just wondered if you could see it in terms of the bulk composition of the rock.
Well, that's a very good question. So when you look at those bipartite segregations, in lower zone A, they're olivine pyroxenites. By the time you get to middle zone, they about 50% oxides. But this is what all we're seeing is that the liquids are the binode goes like this. So the more fractionation you get, the more extreme the two liquid compositions are. So it depends where you are on the binode.
But in these layers that you want to say that the liquid is settling down into, can you look at that bulk rock composition and say that it's 50% original oxide plus whatever else plus some fraction of.
Yeah, that's the next thing to do. Yeah. So how much is this? How much is interstitial liquid? I'd need chemical maps.
Okay, I think we have two last questions before we break. We can continue later on.
Yeah, you can
With
back
Matt and then John.
Just a quick comment to come back to the viscosity issue. So you're absolutely right. It doesn't affect the final equilibrium configuration of the fluid phase saturations. It would just affect the rate at which you approach that new equilibrium configuration. And so having actually done capillary invasion experiments, if you do them with air and water, they're really fast because you've got relatively low viscosity. If you do them with water and a very viscous crude oil, it just takes a lot longer for you to reach the new equilibrium. The final configuration is the same. You'll be controlled by the more viscous.
The discussion will play.
Yeah, it controls the rates.
And that's what I'm talking about.
Yeah.
That's fine.
John?
So Marian, I think someone said there's two certainties in life, death and taxes. Not taxes, taxation. Third certainty is that a seminar where you would say no compound. No, so here's a rock and there's no compaction. But you did say today there's another part underneath the block, but lots of compaction.
Yeah.
Do you have a picture of that rock? What does it look like? Does it have all deformed magic phases and fractured grains and so on?
No, we did a preliminary experiment. We had a postdoc who didn't finish the work, and we deliberately sampled under the blocks and then the same layer further away. And the amount of deformation is really not very visible. So I think it's a mechanical rearrangement rather than viscous compaction that we're seeing. That's how the layers get thin. The grains are being shunted. Is this happening when there's such a high amount of liquid there that it's like Lego bricks, you can shake them around and the